Microwave bench, attenuation and Q measurements. Series on microwave engineering, lecture number 6.18. Attenuation is a signal conditioning, a process in which strength of the signal gets reduced. It is inverse to amplification. To amplify signals, we use amplifiers. Attenuators play an important role as much as amplifiers play in the design of communication systems. Any passive component, any passive device, any passive circuit, it provides, it inflicts attenuation over the signal when it is passing through it. Of course, when signal is passing through active circuits like amplifiers, the signal strength gets enhanced. In the present session, the focus is on methods that are available to measure attenuation offered by a microwave component, offered by a microwave device, offered by a microwave circuit using a microwave bench setup. This session also covers the topic measurement of Q with bench. Q stands for quality factor. Quality factor of a coil. A coil, it is supposed to give inductance. An ideal coil, in fact, gives only inductance. No resistance, no capacitance exists with the coil. However, if we consider an ordinary coil or a coil in the real world, in it one can find, in addition to inductance, it also exhibits certain amount of resistance, sometimes even capacitance. Presence of resistance, presence of capacitance, they indicate non-ideal nature of the coil. Their amounts give certain information regarding the distance of practical coil from an ideal coil. How far a coil is near to an ideal one, or how far a practical coil is away from an ideal one. This aspect is measured by one parameter. It is Q factor, quality factor. Quality factor can also be used to describe capacitors. They are also used to describe the quality of a resonant circuit, which is a combination of L and C. Cavities are resonant circuits at microwaves. Q is used to describe, to indicate how far a practical cavity is near or far from an ideal cavity. Then one may wants to know what is ideal cavity. Cavity consists of two parts, enclosing wall and enclosed volume. If the enclosing wall is made with perfect conductor, which doesn't exist in reality, and if the enclosed volume is a perfect dielectric, implying conductivity 0, of course, which doesn't exist in reality, then that cavity is an ideal cavity, a perfect cavity. Otherwise, it is non-ideal cavity. Q factor gives an indication regarding the distance of ordinary cavity from ideal cavity. In the present session, after covering attenuation, we cover measurement of Q of a cavity with microwave bench. Let us move further into the core session. As introductory remarks to the session, a few points on attenuation. Attenuation is a parameter which actually is inverse of gain, and more or less all passive devices that are in the path of the signal inflict some amount of attenuation over the signal. Two methods are being explained here for the measurement of attenuation at microwave frequencies with the bench. One is called power ratio method, which uses a power meter, and the second method is called substitution method. Both the methods, they are described, explained here in an elaborate manner. First, power ratio method. The device for which attenuation is to be measured, it is placed before the slotted section of the bench and terminated with matched load. The output of the tunable probe is then connected to a power meter. It gives an indication of the power in the wave. Let us suppose the indications of the power meter are P1 and P2 with DUT and without DUT. With DUT P1, without DUT P2. DUT stands for device under test. It is this device for which we want to know the attenuation. Then the attenuation A in dB due to DUT is given by, it can be found using this formula. A in dB is equal to 10 log P2 by P1. P2 without DUT. P1 is with DUT. Naturally, P2 is more than P1 because presence of DUT inflicts attenuation over the signal. So power reduction happens when DUT is there in the circuit. In this technique, the absolute values of powers are not necessary. What we want is attenuation. This attenuation can be found, or it requires ratio P2 to P1 ratio. Absolute values of powers are not required, only the ratio. The ratio of powers is sufficient. Therefore, power meters are not necessary. Power meters are not a must for carrying out this measurement process. In case of non-availability of power meter, the power ratio can be obtained by connecting the output of tunable probe to a multimeter or CRO, once with the DUT and once without DUT in the bench. So in place of power meter, one can use multimeter or CRO. Bench setup. This is the bench setup. Source supply, source, isolator, attenuator, matched attenuator. Usually flap attenuator exists here. Output of attenuator is to DUT. From DUT, the signal goes to standing wave detector, which is terminated over a matched load. The tunable probe output is connected to power meter if power meter is available. Otherwise, you can connect it to a CRO or a voltmeter, ammeter kind of thing. We have to take readings once without DUT and once with DUT in the bench setup. By applying 10 log to the ratio of voltages or currents, the required attenuation can be obtained since the detector of probe obeys square law, leading to P1 by P2 is equal to V1 by V2 is equal to I1 by I2. Notice, tunable probe output is connected to power meter, and using power meter, one can find P1 and P2. They can be substituted in the formula and find out attenuation. If power meter is not available, tunable probe output may be connected to a CRO or a voltmeter. Voltmeter or CRO gives voltages without DUT and with DUT. If it is CRO, you can find current also. Once with DUT and once without DUT. Those currents and voltages, their ratio is related to ratio of powers P1 to P2 through this relation. This relation P1 by P2 equal to V1 by V2 equal to I1 by I2, it is a consequence of detector obeying square law. There is a drawback with this method. There is a built-in inaccuracy in this process, which uses two different points on the characteristic curve of the diode detector, where the detector may not be obeying square law characteristic, leading to erroneous readings. What is the meaning of this statement? The detector that is there to detect the wave in the slotted section. This detector, it is not always obeying the square law. It obeys square law only over certain portion of its characteristic curve. That too approximately square law obeys approximately the square law only over a small portion of its characteristic. If the operating point is below the characteristic or above this small portion of the characteristic, then deviation from square law becomes huge. We are making the measurements at two different points. These points may be one below the portion where square law characteristic is obeyed. One may be above the portion where square law characteristic is obeyed, at least approximately. In such case, these two readings which are taken over the characteristic curve of the detector, they are far away from the ideal square law characteristic, resulting in huge amount of inaccuracy in the result, huge amount of error in the result that is obtained with the procedure mentioned here. Precaution. Both the source and attenuator should remain undisturbed so that the wave is at the same power level and frequency in the standing wave detector until the completion of the experiment. Another method, RF substitution method. In this method, the inaccuracy that exists in power ratio method is eliminated, at least to some extent. The DUT is placed before the slotted section and the tunable probe output is connected to power indicator like power meter, VSWR meter or multi-voltmeter or CRO. As VSWR meter is most available in the lab, it is used frequently. The bench is terminated with matched load. After completing all the necessary adjustments with the source, attenuator, etc., the deflection of the pointer in the VSWR meter is to be noted down. This is the bench setup. Source supply, source isolator, matched attenuator. Like several other experiments, this experiment or this method also has two parts. In the first part, DUT is in the circuit. In the second part, DUT is replaced by a standard attenuator. So DUT or standard attenuator output is connected to standing wave detector and tunable probe is output is given to power indicator. Standing wave detector is terminated with a matched load. So first with the DUT, then with standard attenuator. In the next step, the DUT is to be replaced by with a standard variable precision attenuator. Its attenuation is to be varied until deflection of the pointer is the same as that in the previous step. At this position, the attenuation of the standard attenuator, which can be noted down, gives the attenuation of the DUT. It is substitution method. In the name itself, the steps, the method that is followed is indicated. Precaution. Both the source and attenuator should remain undisturbed so that the wave is at the same power level and frequency in the standing wave detector until the completion of the experiment. Now we move to measuring Q with the bench. Q of a cavity. The quality factor or Q factor is an important parameter indicating quality of resonant circuits and cavities. Cavities are actually resonant circuits at microwave frequencies. At small frequencies, a parallel LC circuit, it acts as a resonant circuit, but this fellow fails to work at microwave frequency. Here, cavities are used. Cavities work as resonant circuits. Q actually denotes the frequency selectivity of a resonant or anti-resonant circuit. By definition, it is 2 pi maximum energy stored by energy dissipated per cycle. It can be shown equal to omega means angular frequency. Maximum energy stored by power dissipated. It can be shown it is also equal to the ratio of resonant frequency to bandwidth. Here two methods which are widely used for measurement of Q of cavities. They are described by transmission. This is one method. This method is used when the cavity for which Q is required has two ports or two openings. There are cavities for which there is only single opening. For such cavities, this method is not suitable. It is to be connected before the slotted section in the bench with a tunable source. Tunable source means a source which has a facility to change its frequency. source gives out a wave. If a facility is there with the source or in the source to change the frequency of its output, then it is called tunable source. The termination of the bench must be matched and the output of the tunable probe is given to a power meter. The power that is transmitted by the cavity is measured using the power meter at different frequencies and a graph is drawn. It resembles inverted U. So this is the setup. Tunable source, source supply, isolator, matched attenuator. This is the cavity. Two openings are there, one to accept input, another to give out output. Cavity output is connected to standing wave detector, which is terminated over a matched load. The tunable probe output is connected to power indicator. So the procedure is changing the frequency of the source. Measure power that is transmitted by the cavity using power indicator. Then draw a graph between frequency and power transmitted by the cavity. This is frequency, this is power transmitted by the cavity. If you sketch a graph, it is like an inverted U. Notice power is maximum. Here that power is indicated by PR. PR occurs at certain frequency. That frequency is indicated by FR. Power transmitted falls to PR by 2 at two frequencies. Those two frequencies are called 3 dB frequencies. The distance between them is bandwidth. So we have a set of power values. We have corresponding frequencies. So graph can be drawn. From this, FR can be identified. The distance between half power points also can be identified from the graph. Q is resonant frequency, FR by bandwidth, distance between the 3 dB points. From the graph, the resonant frequency, the frequency at which transmitted power is maximum, and also half power frequencies at which transmitted power is half of the maximum can be determined. Difference of half power frequencies gives bandwidth. Q of cavity is related to resonant frequency and bandwidth through the relation Q equal to resonant frequency by bandwidth. Precautions. Both the source and attenuator should remain undisturbed so that the wave is at the same power level and frequency in the standing wave detector until the completion of the experiment. There is another method. This method is suitable when the cavity has a single opening. It is by measuring VSWR. This method measures Q of the cavity by measuring VSWR at different frequencies. The bench with the tunable source is terminated with the cavity and output of the tunable probe is connected to VSWR meter. The VSWR due to cavity is measured at different frequencies and a graph is drawn whose shape is similar to U. This is bench setup. Tunable source. The source must be able to give wave at different frequencies. And also there must be a mechanism by which we can know the frequency of the wave. Of course, to know the frequency, here you can insert wave meter. In the previous method also, in the method by transmission, there also, to know the frequency of the wave, one can insert a wave meter after matched attenuator. From wave meter, frequency can be noted down. From VSWR meter, VSWR can be found. Cavity has a single opening here, so it is connected to the standing wave detector as its termination. If we sketch a graph between frequency and standing wave ratio, we have standing wave ratios for different frequencies. Using those sets of values, one can sketch a graph. It appears like U. It is in the shape of U. SWR assumes minimum value at a frequency. That frequency is FR, resonant frequency, and it can be noted down easily from the graph. That is value of FR. The frequency at which VSWR is lowest, the resonant frequency FR, and also the lowest VSWR, that is rho R value. Both can be noted down from the graph. From the lowest VSWR rho R, using one of the following relations, one can find half power VSWR rho half. This quantity has to be calculated. this value. It has to be calculated from rho R and FR. Rho stands for standing ratio. Rho half is equal to rho R plus 1 by 2 rho R plus square root of rho R square plus 1 by 4 rho R square. Either this relation or the relation given just below. The rho half equal to 1 by rho R plus rho R by 2 plus square root of 1 by rho R square plus rho R square by 4. Using either one relation, one has to find out rho half, this value. Now, if you draw a straight line at this value, you can find this straight line cutting the curve at two frequencies. These two frequencies are 3 dB frequencies. The distance between them is bandwidth. Already we know FR value. Now bandwidth is also known. With the values of these two parameters, one can compute Q. Now, out of these two expressions, which one has to be used? If R is more than Z0, Z0 is characteristic impedance. R is resistance of the cavity. Resistance of the cavity. If R is more than Z0, above relation has to be used. Otherwise, bottom relation, this relation has to be used. Okay. Using the computed rho half from the already drawn graph, the half power frequencies, and from them bandwidth can be computed. Using the formula for Q in terms of resonant frequency and bandwidth, one can easily determine Q. Precautions: both the source and attenuator should remain undisturbed so that the wave is at the same power level and frequency in the standing wave detector until the completion of the experiment. This is what I want to share with you for right now. To recap, measurement of attenuation with a bench. The methodology is described. There are two methods. Both the methods are described elaborately. Then measurement of Q with the bench, it is considered. Here also two methods are there. Both are described in detail. Hope you have a beautiful and wonderful, a successful and fruitful, a transformative, nurturing, joyful session. Enough for now. See you again in another informative session. Bye bye.